In this week's lesson, we are going to discuss addition. We are going to begin by examining 4 addition problems. Addition problems naturally occur when we combine objects or want to know how many. We're going to look at the following 4 addition problems, and you're going to write your responses to the questions in your own words. I want to know what action words describe what is happening in these and other addition problems. For example, the action word combining. What other verbs can you think of? And other than they all involve addition, can you think of other ways in which the 4 problems are alike? And in what ways are they different from each other? Problem 1. Andy has 3 marbles, and his older sister Bella gives him 5 more. How many does he have now? When we look at this problem, we are given information to start with. We're starting with a solid 3 marbles. So we have concrete objects. We can have a one-to-one correspondence. How many does he have after Bella gives him 5 more? Problem 2, Keisha and Jose each drank 6 ounces of orange juice. How much juice did they drink in all? Problem 3, Linnea has 4 feet of yellow ribbon and 3 feet of red ribbon. How many feet of ribbon does she have in all? Again, in this one, we are combining a length of ribbon. Josh has 4 red trucks and 2 blue trucks. How many trucks does he have altogether? One of the themes of our textbook, as well as the learning standards, is the power of multiple representations. Here we see examples of diagrams that we can draw in order to represent the 4 addition problems. On the surface, they seem quite different. We have the marbles that represent problem 1, the 3 marbles, and then the 5 additional marbles given to us by our sister. We have the ounces of juice measured with a scale. This looks like a tape diagram where we identify the number of units represented from the whole. We have feet of ribbon. This looks like a number line, a horizontal number line. Then we have pictures of trucks. We have the 4 trucks, the 4 blue trucks, and the 2 red trucks. In each of these cases, we're joining 2 sets or increasing the size of a given set. In general, we can represent any addition problem as A plus B equals C. You can see these represented by tape diagrams or these rectangles. The entire rectangle represents the whole, C. We have a part plus a part to equal that whole. This general model is a very simple model, but yet it represents a part plus part equals whole relationship. It captures the way in which all addition problems are similar, joining or combining 2 amounts to make one larger amount. It also relates to the notion of parts and wholes. It's an abstraction that is important in the development of whole number ideas and understanding ideas such as fractions as we advance through the basic operations. This model also works well whether the elements to be combined are sets of a discrete object like the marbles or measurements like the ounces or the feet of ribbon. And as we examine all 4 operations, we're going to see that we can define all 4 operations in this context. It means we're going to see the connectedness of all 4 operations. As we see the connectedness, we can relay this connectedness to students and help them to be more successful with non-routine and multi-step problems. So when we're talking about addition, we can define it in the following way. Addition is disjoint sets combining. So if A and B are disjoint sets containing A and B as elements, A plus B equals N. Part plus part equals whole, which is the union of A and B. If we go back to our set theory notation, we're going to start by representing addition with number lines. It's a simple tool used to help quantify what's happening for young children. It's a tool they're familiar with because many children learn how to count with a number line. Research shows that American school children tend to have trouble understanding and using this model, but number lines are found in real life on rulers, clocks, graphs, thermometers. A number line can be made by taking a line and marking off 2 points, 0 and 1. The distance between that 0 and 1 is our unit. So our unit segment is the distance between all consecutive unit segments is going to be the same. And even though number lines are most commonly used to represent length, they can be used to model all kinds of problems. Let's take our ribbon example, our ribbon problem for an example, because it does represent 2 different lengths being combined. Linnea has 4 feet of yellow ribbon and 3 feet of red ribbon. How many feet of ribbon does she have? We could start by drawing a number line, going from 0 to 7 in this case, but we could go from 0 to 10. We could start off by drawing a line that goes from 0 to 1 to represent the original yellow ribbon, and then increase it by 3 more units, 1, 2, 3 more units until we get to our total of 7. So our part, 4 feet of yellow, plus our other part, 3 feet of red, gives us our whole 7 feet. And that's represented simply on this number line. Or we could just start at 4 on the number line. This is for students who have a more keen number sense, knowing that they can start at the first addend rather than begin at 0 and then move 3 units to the right, increasing on the number line. When we talk about addition, we recognize the properties of addition, the characteristics of addition. We have the identity property of addition. Identity property simply is A plus 0 equals 0 plus A, which is always going to be A. So A, if you have a number and you add 0, you're going to have the number that you start with every time. Adding 0 does not change the answer. We have the commutative property of addition, and that simply means that A plus B is the same thing as B plus A. Changing the order of the addends does not change the sum. The order of the numbers being added does not change the sum. The associative property of addition. When you think of associative, we have the root associate. So we think about groupings. A plus B added together first, then we add C, is the same as if we add B plus C first, and then add A to the sum of B plus C. The grouping of the addends does not change the sum. But, as we'll see later, it can help simplify the process of addition. And then we have the closure property of addition, which means the sum of any 2 whole numbers is a unique whole number. And by unique, we mean the sum will always be the same number. Then we have existence, which means the sum will always be a whole number. Many times when children are learning how to add, we can use tools like the addition table or base 10 table. We use it as a grid system. 1 plus 0 equals 1. That's our identity property. 1 plus 1, where do they meet? They meet at 2. 1 plus 1 is 2. We can also talk about carrying and borrowing. These are terms that I personally do not like. I like the term regrouping. Although carrying and borrowing are terms that you are likely to encounter as you are going through school. We've noted that we often need to regroup when adding and subtracting. That means we have built a group of 10 that we need to regroup as one of the next larger unit. Or we need to decompose a larger unit into 10 of a smaller unit in order to perform the operation of subtraction. What's the same about both of the examples that I'm about to show you is that an amount moved from one place to another always represents an exchange of a 10 for 1. So if we look at 36 plus 28, we would start in the ones. We would have to regroup because 8 plus 6 is more than 10. So we would have a group of 10 and 4 ones remaining in that place value. So now we would have 1 10 plus 3 10s plus 2 10s in order to regroup. Where if we were subtracting, we look at our ones, we cannot take 6 ones away from 4 ones. There's not enough. So we would have to take one of the 10s, decompose it into 10 ones. So now we have 14 ones minus 6 ones. And that leaves us with 5 10s minus 3 10s. It's this process that children need to realize are very identical. They are just the inverse. And a thorough understanding of how those numbers are being manipulated will allow you to complete mental addition. I would like you to complete the following 5 computations in your head, but take note of the strategies that you use to apply, and we're going to put names to those strategies in the next part of this video. 39 plus 57. Again, take note of what you did. 68 plus 35. 66 plus 19. 545 plus 228. 186 plus 125. Again, we'll discuss these strategies in the next part.